All right, so welcome, boys and girls. I am going to be teaching you atomic theory today. My head's cut off. And if the video goes out of focus, please let me know. So atomic theory, we're going to look at the subatomic particles. You had for your first lab, you all watched that video on some of the history and some of the famous people. I wanted to go over an experiment, the gold foil experiment, because some of you had a question about that on the lab. And so I wanted to go over that just briefly. So the model at the time, when I was a young lad, for atoms was that atoms looked like plum pudding, which turns out to not be correct or our current understanding. And so plum pudding is plums in pudding. So they had these islands of positive, and electrons just flowed around the islands, and they were big islands. So this gold foil, does anybody remember who did the gold foil experiment?
Rutherford, right?
Yes, Christian. We'll give him the bonus point today. I had a student last night who asked me, she wasn't able to come to class. She's like, what's the bonus question? I'm like, I don't know. I just asked him randomly. So Rutherford, Ernest Rutherford from New Zealand, he wanted to show this. And so he took these particles called alpha particles. And that the size of the alpha particle isn't as important as the charge. But the alpha particles, he won a Nobel Prize for the alpha particles, not for this experiment. But the alpha particles, because of their charge, he expected when he sent them through that they'd keep running into islands, and he'd just see them all going all over the place. And that was not what he found. What he found, does anybody remember what he found?
It went straight through, right?
Yeah. So 99, like they all went through. They just kept doing the experiment. 99.99999999999. And they keep adding more nines to this. I think they're up to 19 nines. And it will just keep going, an infinite number of nines, because actually there is nothing. And so what this proved is, since they all went through, so no deflection, is that the atom is empty. Meaning empty, there's nothing of material substance. There's no matter. There is more emptiness inside of every atom than there is in outer space. And then every 1 in a million, they would actually see a deflection. And so this screen was made out of zinc sulfide. And so Geiger and Chadwick, I think, were the two guys. They would look for a green blip. And so every once in a while, they'd get a huge deflection, or actually one that went straight back. And what that proved was that there had to be an extremely, that the positive was concentrated in the center. And he coined the term nucleus. So my good friend, Ernest Rutherford, he actually went away in seclusion for 18 months, took his slide rule, did the math, and kept saying, it can't be, it can't be. And so what they came up with is that all the positives, they had not yet discovered protons, but all the positive was concentrated. And it keeps getting more and more concentrated. And the reason he didn't like this is positives, how can they be concentrated? So there's these ideas now, they call them laws, but they're just somebody's ideas. And since they're physicists, they can call them laws. Or if they're me, they can call them laws, that there's these forces that hold the nucleus together. So this is our nucleus. Can you guys see the red pen okay, or should I switch? We'll assume you can see it. But what they found is that positive were protons. And so they had a plus charge. And this is also virtually all the mass. It's again 99.99999% of the mass. The mass being concentrated didn't blow their minds as much as the charge, because it was the electrons and Rutherford kept saying electrons, how they should have behaved is they should have spiraled and crashed into the nucleus, into that positive. And he couldn't understand why. And that's where Niels Bohr, our lecture next week, comes in, is we're going to look at the electron. And Niels Bohr said it is because electrons can only be in specific places. So electrons behave a similar idea as the planets. There are paths around the sun. So the nucleus would be like the sun, and the electrons, like our planet, doesn't get gravitationally pulled into the sun. Our planet stays in orbit. So we had protons, we had the middle one I'm going to put as neutrons, and then there were electrons. They have since found hundreds of more subatomic particles. If you look, you will find there's a whole theory about that. That is probably a law. If you look for it, you will find it. In fact, in our human body, they find new organs every year, which is really weird. So 2 new organs were found this past year. New neurotransmitters are found all the time. Neutrons are called neutrons because they're neutral, and electrons were the first one discovered by J.J. Thomson, third Nobel Prize in Physics. And the charge of a proton and electron are not actually one. Charges are actually given in coulombs. And if you take physics, or when you take physics, you will see that. The mass is the part that's fascinating. And this is, again, relative mass. And I think in the video I gave the actual number, but the mass of the proton and the neutron are 1. We call it an AMU. And the AMU stands for atomic mass unit. You don't really need to know that. It's more, so when I'm using that unit, you can always ask, it's roughly 10 to the negative 24 grams. Now, in all honesty, that can't be measured. That is so small. A grain of salt would be like 10 to the negative 2 grams. Like 1 grain of sodium chloride or a granule of sugar would be like 10 to the negative 2. This is 10 to the negative 24. These guys are called the massive subatomic particles, and they are both found in the nucleus. So that's what you do need to know from this. I talked about it in our Dr. Sherpa talked about it. So these two together are called nucleons because the ON means particle, and then they're particles that are found in the nucleus. The electrons are special. They're found orbiting the nucleus. And next week's lecture is going to be about the electrons. So we spend all next week talking about the electrons. The relative mass of an electron is not actually 0. That is a misconception. It is just really small. It's about, you don't need to memorize that number. You just need to know it's about 2,000 times smaller than a proton and a neutron. And again, we're on these scales that are crazy. So it's like this would be the size of a mouse, and the proton and neutron be the size of an elephant. I think that's what was in the video. And so that's why we call these, the mass is concentrated in the nucleus. All right, I'm going to erase some stuff I put up there, or Dr. Sherpa did, but she wanted to point out, this was before class and people came to my office hours. I am here at 9 o'clock to answer questions, and we were working on the lab. So I encourage all of you to come sometime today. You can stay after class and work on the lab and have me check it off. This was question 6 on the lab, and I made a comment in the lab that you have to show what is given in the question. So the 6 meters times the 3 meters times the 4 meters. And then what I was doing here is showing you either have to change meters to centimeters by cubing that step, or you have to do that step 3 times. And then a cubic centimeter is a milliliter, and you go on from that. So it's just a hint. for doing that question. I walked through it with you. I'm going to move on to the lecture. All right. If you guys have questions, just ask. Now, under this, these particles, these are the only particles we're going to talk about. The current understanding of you humans is that electrons, protons and neutrons can actually have been split, and there's other stuff in them. Electrons have yet to be broken down smaller. The thing that's really cool, which is what those physicists are studying, and I could tell them, is none of them really exist, because there is no such thing as matter. Everything's vibrations. So what's going on in this empty space is actually where everything's going on. And so all of us are consumed with the physical world that we see with our eyes, and it's the vibrations that are in the emptiness. And your thoughts, when they become words, they create the solid stuff that we start seeing. So pick your words carefully, and your thoughts, and your emotions, especially because you have more conversations with yourself than you do with other people, because we're all trapped in our mind, thinking. So be kind to yourself. All right, atomic number. So comments I made earlier to Emily, I would get a periodic table, even just be a piece of paper, and I would put it above your desk. Usually I give out the first, at this day, a hot pink periodic table, and everybody just is hot pink, so you can always pull it out. We use this pretty much every class from here on out, including today. But if you look at your table, and everybody might have a slightly different table, let's talk about carbon. You'll see a number at the top, carbon is 6. And then down below, you'll have a 12.01. This number might have more digits, depending on your periodic table. So the atomic number is this number. So for carbon, it's 6. It is on the periodic table. Every periodic table, no matter what language, that number is going to be the same for carbon. The symbols for carbon may be different. Everybody's gone to this English alphabet symbols now. It's a little bit too bad, because, and this is the number of protons. That's what you guys have all figured out finally. The atomic number, it's like your social security number, identifies you here as a U.S. citizen, is your social security number. This number is the identification of what atom you're dealing with, or what element. So any element found in the universe that has 6 protons, we symbolize as carbon. So if I asked what element has 12 protons, you would look at your handy dandy periodic table, you'd find the number 12, and you would say, oh, that is magnesium. And we're going to do practice on the next page. All right, the mass number, this is what is taught incorrectly by a lot of places on the internet. The mass number is not on the periodic table. And you're all going, but what's that number down there, Captain America? That number down there, you can see, I'm assuming you guys can see, that number is the atomic mass. It is a measurement. It is mass. It is an actual amount of grams of the compound. The mass number will be given to you, and we'll see when we do practice on the next page. It is the number of nucleons. And so because of that, it has to be a whole number. You cannot have a fragment of a proton or a fragment of a neutron. They can only be whole numbers. We can split them and then they're no longer a proton or neutron. But mass number, atomic number are always whole numbers. This down here, that is different. That's the actual mass that somebody figured out and can be measured. All right, questions, because I'm going to change
to using the overhead view and sharing my screen. But before I do that, all right. So let's see. Is that right? Yeah. All right. Oh, by the way, these are like really cool cards some students gave me. So there was a guy, whoever wrote this. I have the book actually.
That's a good reminder. And so every element, they have like some information about it. It looks much nicer. But he did these pictures of every element. So like for hydrogen, hydrogen is the whole universe. He has, I think that's from the Orion Nebula, where, yeah, the creation of new stars. For carbon, that was the bonus question the other day that several of you got. So that is diamond, one of the allotropes of carbon. There's several other ones. So graphite, what you write with. Graphene is actually considered one also. So it depends on what website you went to. It was fascinating because everybody who answered that question gave me a slightly different answer. So everybody had diamond and graphite. And then the two other ones, it seems to be interpreted different. What I heard is graphene, which actually won a Nobel Prize, and it's what's going to make, it's making our phones, it allows you to wear the watch phone. And then the nanotubes came from fullerenes. So buckyball was also won a Nobel Prize, but it's just different ways. And then the different facets of the diamond. Anyway, very interesting stuff. I emailed you a bonus question today. So you should check your email and reply because every bonus point adds in and it allows you, like if you're not able to come on a Thursday, answer a bonus email and that makes up for it. So with that, as of yesterday at 4 o'clock, I took all the bonus points. Some of you had like 4 bonus points and I added them to something, to your quiz. And so I'll do that like every Wednesday when I grade your quizzes, is whatever bonus points I have from the previous week. So like right now, Christian got that Rutherford. So I randomly will ask one in class and then often I'll give you an email one. So check your email, which I know somebody did because they wrote a nice message to me. All right, so periodic table. Let's fill in down here. So again, the atomic number, oh, the Z and the A. I don't like those. Dr. Sherpa talking and Steve Rogers also. He doesn't know who did this either. That's just a designation. We're not going to use those. So atomic number is your protons. And that is on the periodic table. Can't emphasize that enough. And your mass number is your nucleons. From what was on the board behind us, that is your protons plus your neutrons. The symbol for the subatomic particles is lowercase and then their charge. Which was the last one you think that was discovered of the proton, neutron, and electrons? Any thoughts? And why? Be a bonus opportunity again. The neutron was the last one. It actually took them 20 years to find it. They knew it was there to account for the mass. They knew there had to be another particle, but because it's neutral, it does not get deflected in a magnetic field. So the electron and the protons, the electrons were the first. It has to do with deflection in a magnetic field. And that was J.J. Thomson's brilliance. There were other people working on the same thing, but they made the wrong assumption. He made the assumption that everything else built off of. So once they had the negative particle, the search was on for the positive because they knew there had to be a positive. And then to account for the mass, they knew there had to be more. All right, so isotopes are the same elements. We're going to go through how to write this. but they have a different mass. So every element has isotopes. And so what that means, same elements, is they have the same protons. So same protons, because the protons tell you what element you have. Different mass means they have a different number of neutrons. So an example would be hydrogen. There are actually 3 isotopes of hydrogen. And this is how we would write them. H1, H2, and H3. So these are isotopes. The top number is the mass number. So they each have a different mass, 1, 2, and 3. The lower number is always the same, and that is the atomic number. And this is how we write symbols when we write them out. We write the mass number over the atomic number. And this drives students crazy because on every periodic table, on the table itself, they have the atomic number is always up high. So like for carbon, and the mass number is down below, and drives students crazy. So what it is, if we look at hydrogen, since I'm talking about hydrogen, this number here, on mine is 1.008, sorry. So we see the H1 and then the 1.008. This number is the average of all the isotopes. So it's the average mass of the isotopes. And we'll do a question with that on the next page and we'll see. But so for right now, that's an average. When I ask mass number, it is specific for that isotope, and I have to give you the mass number. And so it's shown there. All right. This first question. Oh, Max Planck, brilliant man. So he was the one who took us into the matrix. He actually coined the term matrix and made a huge step, which we'll talk about next week because that gets us into the quantum world. He opened up the capacity for us to go into quantum. And yeah, said also nothing's there, nothing's real. So I gave you I posted a periodic table, I think under week 1 and week 2, which was this one. I like this one because it has all the names on there, but I would encourage you to learn the names or to become familiar with them. You don't have to remember the order, but that way when I'm talking about sulfur, you're not trying to find it. You know that sulfur is S. Or like on our example up here, when you see Ca, so for right now, you'll be searching on your table. And I would post it on the wall above you because we use it for everything from here on out. Ca is calcium. So a question came up from my class last night, and they said, are we allowed to have a periodic table with the element names on it? And absolutely, because half of you are going to do that on quizzes, on tests and quizzes. I don't have the capacity to regulate that. And so let's all just be on the same ground. However, it will make your life a lot easier if you become familiar with all the names. You're not always trying to look and read and stuff. Right. Now you might notice in my symbols in this chart, I didn't show the lower number. And that is because you have a periodic table. The lower number is always on the table. The atomic number is always there. So calcium is number 20. These two pieces always go together. They give you each other. The mass number must be given. And it is. It is this upper number, this 40. All right, the 20, it also goes with the protons. So your atomic number is your protons. And then to find the neutrons, the mass number is the protons plus the neutrons the atomic number is the protons, so we just subtract that first example. Everything comes out as 20. And the electrons, right now, the electrons are equal to the protons unless I change it. On this chart, they're going to be equal, and then I do change it on the next page.
After your first midterm, we will move into ions, and so the electrons will all change. Yeah, and we'll talk about that in a minute when we get to periodic table. Let's go ahead and work on this chart together. So S is number 16. This 35, these are the two ways to show a symbol. So either you can write the mass number before it as a superscript, or you can write it after as a number. So that is my mass number. So the 16 also goes with the protons and the electrons. And to find the neutrons, we take the 35 minus the 16. You don't need to show the math. I'm just doing it here so you can follow along. So this will be 19. And does anybody know what S stands for?
Sulfur?
It is sulfur. It's the fire and brimstone one. So it's actually in the Bible. It doesn't say sulfur, it says fire and brimstone in lots of places, I'm sure. All right, the spelling for sulfur, it does have two U's. If you spell it with an E, I am not going to mark that wrong. If you spell it with a PH, that's fine. That's a European spelling. It's like on that, the first lab, phosphorus, there's actually 3 different spellings for phosphorus. However, if you spell sulfur, S-O-D-I-U-M, that is sodium, that would be marked wrong because that's a different element. Does anybody know the symbol for sodium?
Na?
Yeah, Damon, you got your elements down. All right, so the next one, here we go, Damon, I'll give you a bonus point if you can answer this question too. What element is the next one?
Isn't it chlorine?
It is chlorine. So how Damon got that, the 17 protons must be, I had to write their names on the board or else I'll forget later. So those points will get added to your next quiz. The 17, the protons must be the atomic number. And then you look at your periodic table and you find number 17. So if you're in a classroom, the periodic table is huge on the wall. That's why rather than being like me where I have to keep shuffling stuff around, having it in front of you. So number 17 is Cl. And Damon correctly said chlorine. By the way, chlorine is spelled CHL. Again, spelling's not important as long as we're close. Chloride is when it's an ion. But again, we get to that. So we said chloride. For the mass number, we would add these two together. So if we add these two together, 17 plus 20, we get 37. What can be really helpful is to write the full symbol. So we write the 37 there. So in this chart, if you notice, all whole numbers. We're going to do the math with the periodic table in about a month. We got to get through all this and all the electron, cool, quantum stuff that's important. And we will finally come back and look at this number down below. I think I have a question on the next page about that number, and so we'll come back and look at it. The electrons, keep them the same as your protons. Positive and negative are the same. All right. So some of you maybe finished the whole chart. The 79 goes with our protons and our electrons. We subtract, again, the 197 minus the 79, and you should get 118 if I'm subtracting right. All right, 79 is gold, AU for Arum. Some people are actually, so you're going to call it gold. And if you want, you can put the full symbol, 197. If you want to put everything, it would be 197, and then the 79 would be down below. And so some students like to write the full symbol, because if you take this minus that, that will give you the 118. All right, the next element is not 120, and it is not 70. 70 is neutrons. We need to figure out the protons, and that would be 50. So if I take the 120, which is the mass, minus the 70 neutrons, that would give me my 50 protons. I do not need to see that math. I just look to see if you have the numbers. And this is not on the study set for Tuesday. The study set for Tuesday is the math that is on your lab to make sure you got the math down. This is on the study set for the next week. The study set for Tuesday actually will show up tomorrow. You guys have your lab today, and so I'm not worried about that. The electrons and the protons are both 50. The element is number 50. Number 50 is SN. And I had a student who would always say, tin is a sin. So tin is SN. And then if we want to complete the symbol, at least show the 120. It's actually really good to do right now, because that will help you to get the idea. This is a whole number. And tin was originally, the Latin name is Sanus, since it's one of the first elements that was discovered and was used in ancient times. So learn those first 36 element names. We use them a lot. You're going to hear me say the element like chromium, but I'll write the symbol CR. And so it's being able to have that in your brain, that you see the CR and you're not like, why is she writing that? That you're like, oh, that's chromium. It's a shorthand. It makes things awesome. We can do another chart on the next page. Is there any questions on this one? This class, you guys, well, we're in the mornings, so everybody's quiet, everybody's shy. Please do ask. Periodic table. Periods are horizontal across. So they're also the row. So this is a period going across. They number the periods going down 1, 2, 3, 4, 5, 6, 7. Next week, when we get into electrons, that actually becomes important. So the second period would be lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. The first period is very short, only hydrogen and helium. There's a reason for that we'll see next week. So families are horizontal. I'm sorry, did I say that? The rows are horizontal. I think I said that wrong. The rows are going across horizontal like the horizon, and the families are up and down vertical. They are also known as groups. All the families have a name. There's only 4 that you're responsible for. And again, your quizzes and tests, they are open note, but we're going to want to organize everything onto ideally one page. And so as you learn it, you'll be able to condense this down. So for the midterm, because your midterm will be during the Tuesday lecture time, it does have a limited time, so you're going to want to have things organized. All right, the 1As, or this first family here, the 1s. Some periodic tables call them the 1As. They are the alkali metals. The 2s, some tables call them the 2As, are called alkaline earth metals. So same word. Don't worry about the spelling being slightly different. That's not significant. It is the word earth. These are actually all very common in the Earth's crust. they also always form solids when you mix them with other stuff. They don't, they prefer to be in the solid form. So earth means solid, and that's why they named them. So sometimes, I'm going to put a parentheses, sometimes they don't show the word alkaline, they just call them the earth metals. The word earth is always there. So here we go. Here's another question for you. Does anybody know what the word alkali or alkaline, they mean the same thing, what that means? People are furiously Googling.
Does it have to do with the pH?
It does. It's the opposite. The easiest definition is the opposite of an acid. So alkali are basic, and these are our common bases. So sodium, if it's put into water, you get sodium hydroxide, potassium hydroxide, calcium hydroxide. So they form the bases. All right, the middle here, these are known as the transition elements. I call them the transition metals because they are all metals. And you will see the common metals that you all knew before you took this class. So nickel, copper, zinc, cobalt, silver, gold, iron, they're all in there. There's a reason they're called transition, and we will see that next week when we do the quantum stuff. All right, the last two families, and again, all the families have names. The last two families we want to know. So 17 is sometimes called the 7As. I mentioned that because people print different periodic tables, and we'll all talk about that eventually. These guys are called the halogens. So the halogenated hydrocarbons were a halogen, fluorine, chlorine, put with carbon and hydrogen, and it made this beautiful molecule that is one of the best coolants that you humans have discovered. And it was used for everything, for air conditioning, in your car, in your refrigerator. And it unfortunately made it up above the ozone, and it destroyed the ozone layer. So Australia has this huge hole over it. So they won a Nobel Prize for figuring this out, and they are banned. They were used also as a propellant. So people had asthma, that was the propellant to get the medication into you fast. And so it was only a couple of years ago that they figured out another propellant. And so it's absolutely banned. And the ozone is actually repairing. So just like our bodies, the Earth actually can repair itself. And I think it's in about 20, 40, 50 years, it will actually finally be repaired. Unfortunately, right now, there's still a lot of CFCs up there. There's actually was a hole this summer above the North Pole. It only lasted for a couple days, and then it closed itself. But it's a little worrisome, right? That means that the ozone layer protects us from UV light, so we only get a little bit. And all right, the last column, 18, is very important. These are the noble gases, not Nobel, like the Nobel Prize, which, by the way, here we go. Here's another email bonus because my other class got it. So you had to respond before our next class, which is next Tuesday. The Nobel Prize in chemistry was actually given out 2 days ago. So if you want to email me who received it and what they received it for, you can all get a bonus point. Look at all those bonus points today, and that will get added to your next quiz. So easy. You do it right now on your phone. I won't know because you're all not there. But the noble gases, they are inert. So someone other than Damon or Christian, does anybody know why they're special or what the word inert means? Nobody wants to play. It means they're non-reactive. The noble gases were not part of Dmitry Mendeleev's original periodic table. They had not been discovered yet. So the noble gases, they don't react. They are perfect. They are serene. Everything else on the periodic table is reacting to become like a noble gas.
Is it because
So
they already achieved the octet rule?
yeah, we get into that actually in like 3 weeks. But yes, that is why, Christian. There is actually another family, and on some periodic tables, they call what's now 10. They originally were called the 8Bs. They are called the noble metals because they don't react. They are the only metal solid that doesn't react, and that is nickel, palladium, and platinum. And that is why people steal your platinum from your car to buy meth. The catalytic converter. Platinum and palladium are extremely useful. And I can't believe people wear them as jewelry because they have a much better use than that. They've actually mined all the platinum and palladium on this planet. And that's happened like in the past couple of years. And so there's a limited amount. All right.
This is also a quick reminder, you guys get into, you're going to do a paper on one of the elements. So there's some cool things. You can always just send me an email or let me know during an office hour if you have one you want to look into. And I've had some people do, so I don't know my superhero stuff. So did Steve Rogers get an element or a compound injected? He got a compound injected in him. I think it's Wolverine has an element. Anyway, there's some mythological elements. Oh, it's my shield. I lost my shield. It's terrible. And the Halloween shields are really expensive, so I'm waiting until after Halloween to finish my outfit. The Captain America's shield is actually an element. So I've had people pick that as their elements. Just to let you know, you can have a lot of fun with this paper. Pick an element that you want to learn more about or that you can do something really cool with. All right. The metals are over on this side. There is a dividing line right here. I have a different colored pen. I do have a red pen. I have red and blue for Captain America today. There is, it's hard, I did not hit the color ink on my printer, and so I got black and white again. But there is a staircase on there. This side are the metals. So everything below the staircase are metals, and everything above the staircase, upper right, they are called non-metals. You guys already know metals tend to be solids. There is an exception. And non-metals, some are solid, some are gas, some are, there's actually one that's a liquid. Metals conduct electricity. They conduct heat. They're shiny. We can make them into jewelry. We can pound them into wires. We can, so all that stuff. So those are non-metals. You can't do that with. The metalloids are also known as the semi-metals, and they are, if you print it in color, if you look at it, they should have been color-coded. We'll color them red. They touch the staircase on two sides. The exception is aluminum. Aluminum is a metal. These guys, the old name was metalloids. The new name is semi-metals because they are the semiconductors. The most common, the most abundant one on the planet Earth is silicon. It is not the best one at doing this, but it is the cheapest because it's sand, is silicon dioxide. So we can take the silicon and we all have this wonderful technology. So we can exist like this in the classroom. So these other ones are also metalloids, semi-metals. Antimony is an interesting one. It's something else that you need to know about families. Actually, I'll mention about antimony. Families behave the same. You might not like that you behave like your family. You might not want to admit it, but we do behave like our family because we're around them the most. And we all have an extended family too. So, but they behave the same, meaning chemical properties. That was how Mendeleev put his periodic table. So the alkali metals are in this family because they chemically behave the same. So we'll put the word chemically behave the same.
And some of the questions on the next page, we'll see that question come up. So with that, going back to antimony, antimony behaves just like arsenic, and probably you've all heard arsenic is a poison. I think that's how Napoleon was killed. Can't remember, some famous people have died from arsenic. Antimony also is, and how I learned
It got its name is it actually stands for anti-monk, that an abbot fed it to his monks thinking it would make them eat more, and it did. They ate more. They were fasting because they were meditating, and he was worried they were going to die from not eating, and so he started sprinkling antimony, and it gave it more flavor, and they loved it, and they ate it, and then they all died. So it is actually also a poison. The Egyptians used it as makeup. It was the black around the eyes that you see was actually antimony is the way that it is actually correctly said, but in this country we say antimony. And the Roman Empire, because they were all going crazy from lead poisoning in the brain, they would use it to make themselves, they would party on all the wine they were making also, and then they would take antimony to make themselves vomit so they could drink more wine. So the Roman Empire is pretty crazy. Not my favorite part of history to go back and look at. All right, we're going to do the last page, unless there's any questions. And yeah. All right. So again, your homework set for next week is the math and this stuff, as well as all the electron stuff shows up on the week after homework. So the week after is a bigger homework set. When you do the lab today, and I highly recommend you get help from me, or ask me if you have questions on it. That should make the study set for Tuesday really straightforward. All right, and a reminder, if you turn the lab in late, you only lose 1 point. So if you don't have the lab, you're you start struggling on the third or fourth page. Every question's worth 1 point. I would rather have you turn it in late and come to an office hour and get help. So you just lose 1 point. But let's just do it today. Let's all get it in today. All right. Same with study sets. You lose a point. There is a deadline. It is by the midterm. At that point, they become 0. Labs are worth a lot. They're 15 points. So this page is actually a really important page. I would reprint this page and do it again. Not today, but like next week. And for the midterm, because it will give you practice. You don't want on the midterms be trying to go through all your notes. You want to just know the stuff. And then probably half of you are moving on to 221. You'll be able to, the first few weeks, just cruise because you'll know this. So chlorine, I'm telling you there are 2 stable isotopes, chlorine 35 and chlorine 37. The periodic table, if we look, I'll actually just write it up here. If you look at chlorine, chlorine is number 17. And underneath it will say 35.45 or 453. This is the average mass of the isotopes. I mentioned that before, but I promised I would talk about it. So if we took isotope 35 and isotope 37, if you take the numbers 35 and 37 and you average them, you would get 36. But on the periodic table, they didn't get 36. And that's because there's one more piece to this. It's the average mass of the isotopes based on abundance. So they always say percent abundance. So if the average is going to come out always closest to the most abundant isotope. So chlorine 35 is more abundant. It's always going to pull the average closer to it. If you look at hydrogen, hydrogen is pretty much right at 1. That's is 99.9% of hydrogen is H1, protium. The hydrogens, they actually gave names to protium, deuterium, and tritium. By the way, just FYI, I have never seen the last Adventures, so don't tell me what happened, because I don't actually care. So I don't even know if I'm alive still. How many neutrons? So we would take chlorine 35. So 35, and we would subtract the 17. So we take the mass number, we subtract the atomic number. So our answer is 18. The reason that works, I don't need to see the math. I'm just working it through since we're in this funky format. The mass number is the protons plus the neutrons. It's the nucleons. The atomic number is the protons, so that will leave us with the neutrons. So with that, comment for you. Sometimes I ask which one's more abundant. Sometimes I ask how many neutrons are in the more abundant one. And so just make sure you read my question. There is up in this falling apart. All right. So, I know the other comment I need to make. The lecture Tuesday is going to have a pre-lecture, and you can watch it after the lecture, but I haven't made the pre-lecture yet because I have to go to school. It's a demo that I do, and it was the last demo I did before COVID, and I did not know none of us knew this was going to happen. I don't watch the news, so I didn't know what was going on around the world. And so I did the demo and I put it away, and I just put it somewhere. I didn't put it away because I said, oh, I'll be back here next week while they're taking the final. I'll clean up my mess back here. And I have no idea where I put it because that was 6 months ago. So Saturday, I'm going to go in and try and find it, or I have to make it all up from scratch. But it's a really cool demo, and it goes with the quantum electron stuff. So it will be on our class list, and it will be with the notes. When I post the notes, I'll put a link in. But you can also watch it after the lecture. All right, so using our periodic table, fourth period earth metal. The earth metals, again, are in group 2. Again, sometimes use the full name alkaline earth metals, but usually just earth metal. So fourth row, 1, 2, 3, 4, and second column, so Ca, calcium. So we're looking for the name. The symbol would be Ca. For the symbols, I've mentioned this before. If there's 2 letters, the first one's capital, the second one's lowercase. With chlorine, I always write it like this because otherwise people get confused and think I wrote carbon and iodine. All right, fourth period, group 4b. That is actually titanium. Some of the periodic tables do not have the old A and B notation. This issue just happened this year to me because usually I give you this periodic table. It's got writing over it because, yeah, that's what we usually use. So we will fix that. And all right, so this is titanium, which is currently called group 4. And the is a Ti. Tin again is Sn, titanium is Ti. All right, properties similar to sodium. So sodium is Na. You just want the same family. So you can pick any element in the family that you can spell the name of. So just note same family. I'm going to pick lithium. If you want, you can pick Rb, which is like rubidium. All right. So there's some of them have more than one possible answer. Halogen is 17 family, fifth period. So fifth period, if all the way over here, we get to I. So I is iodine. I know it is after 36, but you guys have access to all the names. So that is iodine. Just the symbol I. So if there's only one letter, it is just a capital letter. All right, the third period, alkaline metal. The alkaline metals are the first period, the first column. And we find the third one down, and that is an A. And so hopefully you see that symbol, you go, oh, that's sodium. So even though you have access to all the names, just know them, because that's really what this class is about. It makes the conversation flow much better. Unreactive. Hopefully you all are already writing without me. That is the noble gases.
Which was column 18. And then third period, metalloid, there are two answers. So third period again means the row. Oh, I'm sorry, there is only one. Aluminum is a metal. In 3 dimensions, aluminum doesn't touch this line. There's actually 3-dimensional periodic table. There's actually 5-dimensional periodic tables if we really want to go there. Silicon. So Si. And again, period means row. All right. Questions? I just keep going unless you guys have a question. I'm going to pause the recording. Those of you watching at home, I'm going to give you guys 5 minutes, see what you can do with the chart, or you can take a 5-minute break. Those of you at home, pause the video and try the chart. All right, your teacher's back. Captain America got a call on that fancy thing, had run off, save the world. So hopefully you paused me, tried this. And those of you who are here even, you can go back, the video will get uploaded. The video doesn't save until I go off Zoom, and then when I use this overhead, it takes over an hour for it to save the question. And yeah.
All right. You guys can put stuff in the chat. I just don't see it when I'm going through the stuff. And again, I know that the schedule did not list this. And then I've also learned that a whole bunch of people have classes that have no times listed, and then they added times after class started, kind of like I did. That's why you can always watch the videos. All right, so Na is sodium. Learn your elements. And that pen does show up. Atomic number is 11, so that is always on your periodic table. So always have the table in front of you, so that's our number 11 there. The mass number, again, not on the table. I give you the mass number. All whole numbers. This chart is only whole numbers. Protons and electrons will be the 11, so our atomic number is our protons. I do change the electrons down here because I wanted to show you what happens. The neutrons we get by subtracting. So the protons plus the neutrons, these two together give you the mass number. All whole numbers. P is phosphorus. Again, I learned that it is spelled different on different tables. I always learned it as the OUS, but that table that I think is on the notes has it just as US. 35 is the mass number.
Because the atomic number would be number 15. Yes. Which is 15 protons, 15 electrons, and then by subtraction we get the neutrons. If somebody has a question, please just start talking, because somebody else probably has that question. All right, 33 is element 33, and that is AS, and that is arsenic. So 33 would be my electrons. We add these two together and we get 74. And again, the mass number is not 74.92. That is the atomic mass. That is a measurement. And so it has limited sig figs. This chart is exact numbers because we're counting protons, neutrons, and electrons. All right, the next one is not 24. We have to subtract, get 22, 22, 22, and that is Ti, titanium. Now the next one, the 47, is our atomic number. It is Ag, which is silver. The mass number is the combination of these two, so it's 107. So again, the number on the periodic table for silver, 108, would be more common, but I'm specifically using the isotope 107. So there is something that happened on this one. We lost an electron. Sorry. Do not lose or gain electrons unless I do it for you until after the midterm. We'll get to ions. So it has a charge of +1 because it has one more proton than electron. So when you lose an electron, the charge actually becomes positive. We show charge after a symbol as a superscript. If it's a +1 or a -1, they just show the plus or the minus. You can show the 1, but nobody does. If you want to show the full symbol, the 107 mass number goes above previous, before the symbol as a superscript, and the 47 is a subscript.
So that would be the full symbol. I'm okay though with just the Ag plus. Right, the next one, the 35, is our element 35. We subtract to get the 44. So again, the 79 minus the 35 is where I got the 44 from. And this one has an extra electron. So it gains an electron. So when we write the symbol for 35, it is Br, and to show an extra electron, we would put a negative, and Br is bromine. All right, sorry, too many things on my desk. So this last question is a tough question. It shows up on your study set 3 in 2 weeks. So I put it also on our notes, so hopefully it will help you. And you'll probably see a question like it on your midterm. Not next week, in 2 weeks on Thursday, I do a practice for the midterm. And so I'll be able to answer questions then better. All right. What these two have in common, if the mass number is the same, so their mass number is the same, that must mean what else is the same, or what is the same about them, given the choices up here, is nucleons. That's what you were all going to say. So same number of nucleons. I'm going to skip to C. On C, they are the same element. So usually our answer for same element is same protons. But that was not a choice up here. So if they have the same protons, what else must be the same here?
Neutrons?
Not neutrons.
Electrons.
That's actually what's good. Electrons. So they have the same electrons. What are these two called? What was that fancy word? So they're the same element. They have different neutrons because their mass is different. So it's a word I used.
Isotopes?
It is isotopes. I don't know who said that. was a very sweet voice. But yes, these are isotopes. So isotopes again are the same element, so same protons, but they have different mass or different neutrons. So yeah. All right. So is that you, Maddie? I don't know who talked.
Yeah, it was me.
All right. I'm gonna give you a chance for a bonus point. I should have on that one, but I didn't know who it was, and your name just finally moved up. Do you know what the answer is for B? We can rule out some of the choices. So we can rule out the nucleons because the mass is not the same. We can rule out the electrons because they're not the same element and neither one has a charge. So to figure out neutrons, what would I do?
You would minus the protons from the mass number.
You would, and we find the protons from our periodic table. So potassium is 19. So if we subtract the protons, we would get 20 neutrons. And for argon, if we subtract 18, then we get 22 neutrons. So the answer must be total subatomic, because the neutrons weren't the same. How do you get total subatomic? So what do you think I mean by total subatomic?
Neutrons plus protons plus electrons.
Yeah, it's all three of them. So it is your protons plus your neutrons. Your protons plus your neutrons are your mass number plus your electrons. And your electrons, because there's no charge, is your atomic number. So just be careful. The electrons can change. So if you take your mass number plus your atomic number, you will get your total subatomic. If we subtracted, like Maddie just said, that gave us the neutrons. If you actually instead add, a different color I can use. So if we instead add them,
You get for both of them, you get that they have 38 total. Sorry, 58. So they both have 58 total subatomic. So that was our answer for that one. All right, any questions? I'm going to stop recording unless there's a question.